Yo, what's good, math fam? Let's talk transformations of rational graphs. This is where algebra meets motion. We're taking the parent function, 1 over x, and shifting it, flipping it, stretching it, basically remixing the graph to show how each part of the equation changes the shape. Vertical shifts, horizontal moves, reflections, and asymptotes. It's all part of the story. So grab your graphing skills and let's transform the way you see rational functions. Let's get it. All right, transformations of rational graphs. We always start with the parent function every time we introduce a new function, and it gives us a good starting point. So when we start to transform the graphs, it's always best to start with the parent function. All right, this particular type of function, rational graph, looks a certain way. But there's different variations of it, right? There's multiple variations. So we're going to look at the first most basic rational graph. So the most basic rational function is 1 over x. Y equals 1 over x. So what does this look like? You can pause the video and fill out the chart. I'm going to do it fairly quickly here. So whatever x is, it's going to go into the denominator, 1 over that number. Right, so this is going to be 1 over -3, -1/3 basically. And then again, you can fast forward through this or pause it and fill this in. 1 over -2, 1 over -1, which is basically 1 over 1, -1. 1 over 1/2. That's going to flip the denominator to -2 basically. This is going to be -3. 1 over 0. 0 in the denominator, this is undefined, right? We don't have, there's no value for 1 over 0. We cannot divide by 0. I know this is going to go kind of quickly, but I mean, you could put all this in the calculator and understand. Because once we get all these points, when you plot them, really, it's understanding what the graph looks like, right? And we're looking for accuracy of what the graph looks like, not necessarily precision, but we're going to be precise on this first example. Our 1 over 3 will be 1 over 1 over 3, would just be 3 because it flips. This would be 2. 1 over 1 is 1. 1 over 2, 1 over 3. So basically what's happening is that if we plot all these points, -1, 2 1/2, 3 1/3. All right. So when you plot all these points, basically, you're going to get all right. Connecting the dots. All right, so notice this particular branch, as we call it, rises towards the y-axis, but it never actually crosses the y-axis. And as it goes out towards, as x goes out towards infinity, the graph will get closer and closer to the x-axis, but it'll never actually cross the x-axis. There's a very particular word for that, which we'll talk about here in just a moment. So this is going to go down, and this is going to go left. Okay, so what's happening? So these graphs, we refer to these, I refer to these as branches. I don't know if that's what they're actually called, but that's how I was taught. So the branches, right, of the graph go towards the infinities. but they never actually cross the X and Y axis. Now, in another video, we'll go into this in a little bit more detail, but for the moment, the blue lines that I drew in, these are called asymptotes, right? Every rational function graph will have asymptotes, vertical and horizontal. Now, there's going to be remember I said there's other variations of this, other versions of this graph. There may be multiple asymptotes, right? But for the most part, the most basic one, this one that we're talking about, it has an asymptote at x equals 0 and y equals 0. So this is it. This is the parent function for 1 over x. 1 over x. I mean, it's kind of interesting. The domain is going to be from negative infinity to infinity minus where the asymptote is. So it's going to go from negative infinity, right? This is x's, up to 0, not including 0, because it's not defined at 0. Union 0 to infinity. The range is the same thing. It's going to go from negative infinity up to wherever the horizontal asymptote is, and then 0 to infinity. Okay, now I know you just have to kind of take on faith right now that this is where the asymptotes are. We'll get into more later on why they're there, but for the most part, just at x equals 0 and y equals 0, they're asymptotes for the parent function. Now, obviously, once you start to move this graph left, right, up, and down, these asymptotes are going to move. And the most basic, not most basic, but what we taught in previous videos about transformations, right? Inside lies, outside tells the truth. Inside is your horizontal left and right movement. Outside the vertical or outside of the parentheses is your vertical up and down. All right. So another version would be 1 over x squared. So this is very, very similar to 1 over x, except you're squaring x squared. Again, you can pause the video or fast forward as I work through these. I'm not necessarily going to explain what I'm doing. I'm just going to do it fairly quickly because all we're doing at this point in the game is just squaring whatever the x is on the table. You just square that number, right? Negative 3 squared is 9. So this is 1 over 9. Right? Anytime you square a negative number, it becomes positive. So this is going to be 1 over 4. 1 over 1 is 1. So 1 over 1/4. That flips. 1 over 1/9. That flips. Again, division by 0 is undefined. We'll abbreviate. I won't be lazy. We'll write it out. Undefined. 1 over 1/9. That's going to flip. This is going to flip. You can start to see a pattern. For sure, a pattern starts to build or starts to become apparent. 1 over 9. 1 over 3 squared. Okay, so here, what's happening is that since you're squaring the denominator, it's making all the values positive. So really what's happening, if you look at the one we just talked about, these or this branch here is basically going to reflect up. All of this becomes positive is essentially what's happening. Now, some of the values are different. That's fine. But look-wise, right, aesthetically, it's going to look with this flipping up, right? It's going to be up here like this. Now, obviously, I'm going to get the details a little bit more precise here because we have different values, but the overall shape is going to look like that. Okay, so let's start graphing this. This is going to be 1, 1, 2, 1/4, 3, 1/9, 2, 1/4, 3, 1/9. Now this is 1/9 is closer to 0 than 1/4 is, right? You can put in a calculator. and get a decimal value if you want. But 1/4 is a quarter of the way. 1/9, it's even closer. And then it's going to have its counterparts, but negative. All right. Connecting the dots. This one's slightly steeper than 1/x. Right, it's slightly closer to the x-axis and y-axis. Again, it never crosses the x-axis. It's like an airplane that's never landing. Okay, so now let's talk asymptotes. The asymptotes is the x-axis or y-axis that I'm drawing right now. Right, it's a dotted line. And then the x-axis. So the graph is going to get infinitely closer to the axes, but never, ever, ever touch or cross. Okay. So there it is. That's 1/x squared. Again, two different variations. 1/x, 1/x squared. Now these get way more complicated, but it's not bad, which again, we cross that in a later video. So the domain for 1/x squared is going to be from negative infinity up to the asymptote, which is 0, union 0 to infinity. The range in this case, it's not coming from negative infinity. The graph doesn't exist below the x-axis. So it starts at 0 and goes up towards infinity. All right, and here they are. These are the parent functions. 1/x on the left, 1/x squared on the right. Again, once these start to get more complicated, they're going to look like this, but there's going to be things added to it. So there's multiple variations of this, which, you'll see. All right. You want to read this? This basically tells you what an asymptote is. I'm not going to insult you. We've talked about asymptotes multiple times in other videos. You can pause and read this if you want. Okay, so if you read this last statement, there is either an asymptote or there is a hole in the graph, which we'll cross that later. We'll bring that up here in a minute. All right. Are there any asymptotes in the graphs above? We already said yes, there is. What are the equations for the asymptotes? Okay, so the asymptotes are going to be, for these particular graphs, x equals 0 and y equals 0. Right? X equals 0 is the vertical. This is the vertical, and y equals 0 is the horizontal. All right, has one of each. How are the asymptotes related to the excluded values we found when we solved rational equations? All right, so if you think about it, when we did rational equations, if you have the opportunity to see those videos, we look and see when the denominator is 0, right? When the denominator is 0, we exclude those values because you can't have division by 0. And that's exactly what we did here. When you have division by 0, there's no definition, right? There's no y value. Like we can't even comprehend what dividing by 0 is because it's not in the scope, right? It's not in the realm of things that we know, right? It doesn't exist. There's no definition for it. It's undefined. That's why there's an asymptote there. So when you divide by 0, wherever that happens to be at, you have an asymptote, right? Every other x value is well defined. No matter what x you pick, you can go up to the graph. When you go to x equals 0, there is no graph. It's an asymptote. It's not defined. All right. So now let's talk about moving it around. So when you transform these, your typical transformation rules apply, right? Inside always lies. what do we consider the inside part? The inside part is going to be whatever's next to the x, right? It's always opposite of what you think. X minus h is going to shift to the right if h is a positive number, right? So x minus 3 would go left, x plus 3, or x minus 3 would go right, x plus 3 would go left. Here we have in example number 1, we have x plus 3. So this is the inside part. This is going to be a shift to the left, 3 units. So notice, right? This is just 1 over x plus 3, not x squared. So it's going to be this version. We take this, shift it left 3 units. Sorry. So the asymptote, which was normally at x equals 0, goes left 3. So here's the asymptote. Horizontal asymptote, right? That doesn't change. And notice I kind of glazed over it, but if you have a number added or subtracted, this plus k, this is your up and down business, right? This is your up and down transformation. So we're shifting it left and right, up and down. Here, there is no up and down movement. So it doesn't shift up or down. It stays vertically the same. Horizontally, though, everything's shifted left. Now, all these points, right? In every other function that we had parent function points. I mean, technically that's still the case, but it gets very, very tedious, right? Like, I mean, we have fractions and whatnot. So here, something to consider is just, right, like this, again, this isn't precision. I need you to be able to just regurgitate and quickly come to the conclusion that this is what the graph is going to look like, right? They don't even give you tick marks. So you're free to just kind of eyeball it. Right, at the end of the day, this is what you need to draw. Right, this is, for the most part, right now, this is good. Like, this is good. There are some details about, where it crosses the y-axis. Again, that's for another video. We just need you to be able to come up with this picture right here. The domain is going to be right from the left, negative infinity, up to the asymptote, which is going to be negative 3. Union, it's going to go from negative 3 to infinity. The range, negative infinity up to 0. Union, 0 to infinity. Right, so think of it like this. I mean, one way you could think of it is I don't know, I want to write this if I want to show you, but you could say all row numbers, but x does not equal negative 3. Right, all row numbers, y does not equal negative 3. I mean, this is more of like, I guess, set notation minus the curly brackets. Interval notation is typically where you want to be at. Just write it in interval notation with the union. Okay, number 2, 1 over x minus 4, all of that squared. Try to pay attention for when you see the square, right? Because the square is going to tell you how it's going to look. Right, so it's going to look like this guy, but just shifted. So which way are we shifting? Inside lies. We're shifting to the right. So everything goes to the right. So 1, 2, 3, 4. Again, this doesn't have to be precise. But we want it to be accurate. And then there's no up and down. All right. That's not to scale, but this is how it looks. This is it. Domain, negative infinity, up to 4, union, 4 to infinity, and then the range, 0 to infinity. Right, it's above the x-axis. Okay, let's keep it moving. Okay, we have a couple more things, a couple more layers being added on. So right here, number 3, looking at this rational expression, we have a negative in front. So a negative typically reflects it down, right, across the x-axis, I guess is the more proper term. It reflects across the x-axis. And then the 2 is going to stretch everything by a factor of 2. So it's just going to get steeper. All right, so let's see if we can graph this guy. So there aren't any left and right movements or translations, right? So the asymptotes don't move. That's kind of a good thing. Not a good thing, but as far as like graphing it goes. All right. There are my asymptotes. And the square is basically going to get flipped down. I mean, I don't want to spend too much time because there's 3 other videos about graphing. So we just need to skim the surface. So there it is. I mean, if you wanted, we could make a table and plot some of these points out. But, you know, this isn't precision. So domain, negative infinity up to the asymptote, which is 0, 0 to infinity. And this is going to be negative infinity up to 0, right? Because it's flipped down. Reflected, I guess you could say. It's reflected down. Okay. Number 4. What movement is this? It's up, right? It's going to shift up 3. This one was reflected and technically stretched. Stretched. Okay. We're going to shift up to 3. And nothing left and right. No movement. Okay, it's 1 over x. 1 over x. It's already burnt into my mind on which side. So, again, future video, we're going to talk about how to find certain precise details. But right now, we're just looking for rough sketches, right? Just an idea of how these look. Negative infinity up to the asymptote, which is 0. Union 0 to infinity. the range, negative infinity up to the asymptote. Here in this case is 3, union 3 to infinity. Right, every number minus the asymptotes. All right. We got a couple more and then we'll call it a day. I'm not going to go into the inequalities in this particular video. We'll save this for a later video. We just need to know how to graph today. All right. Well, feel free to pause the video and knock these out. But in the meantime, this is going to be inside, right inside lies. So this is a shift to the right. 1. Vertical. We're going to go up, right, because it's plus 2. And then we're going to stretch it, right? Anytime you multiply, right, 2 being in the numerator, this is the same as like saying 2 times 1 over 1 minus x, right? If this was, some sort of other equation, you would say, oh, the 2 is in front. This stretches it, right? It's the same idea. So that 2 up top, this is just a stretch of 2, which right now in this particular, keep putting the T after the C, stretch by 2. Okay, in this particular video, we're not really too focused on the stretching part. We just need to understand what left and right and up and down looks like. So we're going to the right 1. We're going to up 2. So 1, 2. All right. There's a branch here. And then there's a branch here. Now you may say, is the branch always in the upper right and the lower left? Yeah, it is. Unless there's something added, right? Unless there's a negative, or if there's some sort of negative added in and it'll reflect it. But again, we'll cross those later. Okay. I guess to be complete, the domain, if you've already answered it, x is going to be negative infinity up to 1, union 1 to infinity. Range is negative infinity up to 2, union 2 to infinity. The equation for the asymptotes, the vertical one, x equals 1. The horizontal one, y equals 2. So you can leave that up for like a little reference. All right. We're almost done. Let's see if we can get less than 30 minutes. All right. We're going to go left 1, down 2, stretch of 3. So left 1, down 2, put in the branches. Top right, bottom left. No, it's squared. Top left. Right, because of the square. Right, because of the square, you have to. So you got to catch yourself, as I did. Whenever there's a square, this is like the branches come together. The branches come together when there's a square. All right. So hopefully you learned something. I'll catch you guys in the next video.